Ever stop to think about how people got around before GPS? I mean, even before the magnetic compass was a common thing. Well, today we're digging into a seriously brilliant and kind of mysterious solution from the ancient world. It's a machine that could literally remember a direction.
So just imagine this for a second. You're trying to cross a huge, unfamiliar landscape. No road signs, no satellites, nothing. How in the world do you keep your heading? This was, a massive challenge for ancient travelers, and the answer that came out of ancient China is it's pure genius.
And this was the solution, the south-pointing chariot. It was basically a two-wheeled vehicle, and on top, there was this little figure. So you'd start your journey, you point the figure's arm south, and then you just go. No matter how many times you turned left or right, that little arm would stay locked, always pointing south. It honestly sounds like magic, but it was all just incredible mechanical engineering.
Okay, so how did it actually work? Well, to really get the genius of it, we've got to shift our thinking a little bit. This thing wasn't sensing direction, not like a compass does. It was doing something way, way cleverer. It was a machine that remembered a direction.
Think about the difference here for a second. A magnetic compass is constantly talking to the Earth's magnetic field. It's always asking the question, okay, where's south now? But the chariot? It did something completely different. You set it once at the very beginning, and from that point on, its whole internal mechanism was just asking one question over and over. How much have we turned away from where we started?
So how on earth did it actually do that? Well, the secret, amazingly, is all in the wheels.
The whole invention really hinges on this principle we now call differential motion, and it's pretty simple when you break it down. When you take a corner in your car, the wheel on the outside of that turn has to travel a longer distance than the wheel on the inside, right? That means the outer wheel has to spin faster. And that difference in rotation, that is the secret ingredient to the whole thing.
Okay, so let's walk through it. The chariot starts to turn a corner. Those two wheels, they start spinning at different speeds. Now inside, there's this really clever system of gears. Most people think it was an early type of differential. And its whole job is to measure that exact difference. It then uses that information to turn the pointer on top in the opposite direction of the turn by the exact same amount. So the turn gets perfectly canceled out in the pointer, it stays locked on its original path.
So the most important thing to get here is that the chariot was constantly doing math. It was performing a calculation as it moved. It was physically computing its own orientation. And that makes it one of history's very first non-magnetic directional memory devices. Just an incredible idea.
But of course, an invention this brilliant doesn't just pop out of nowhere. It takes a person, a real genius, and the engineer who gets most of the credit for its creation was a man named Ma Jun.
Now, while there are legends that place the chariots even earlier in history, the first version that historians can really solidly point to is linked to Ma Jun. He was this famous mechanical engineer back in 3rd century China during a pretty turbulent era known as the Three Kingdoms period. And he was the one who supposedly built a working model when pretty much everyone else said it was just a legend.
But, and there's always a but with ancient history, isn't there? The story isn't totally straightforward. The chariot's exact design is still a really fascinating historical puzzle.
See, here's the biggest challenge for anybody studying this. No original chariot has ever been found. Not one. We don't have any blueprints. All the knowledge we have comes from these ancient texts that describe what the chariot did, but they're often super vague about how exactly it did it.
So we're left with this really interesting situation. We know from the old texts what it was supposed to do, and yeah, modern engineers have built working models based on that differential gear theory. But because no originals have survived, we can't be 100% sure that's how they did it. It's totally possible that different versions over the centuries used completely different gear setups to get the same amazing result. And, we have to be realistic here. This was ancient tech, and it definitely had its limits. For the whole mechanism to work properly, the wheels had to be almost perfectly identical in size, and it really needed flat ground, because any kind of wheel slippage on a rough or muddy path would throw off the calculation. So over a really long journey, these tiny little errors that start to add up, and the pointer would slowly drift off course.
But look, those limitations don't make the achievement any less amazing. In fact, they kind of lead us to the most powerful way to think about this device, not just as a chariot, but as an actual analog computer on wheels.
Just think about it in modern terms. The difference in how the wheels were spinning, that was the input. That complex nest of gears inside, that was the processor, constantly running a calculation. And the direction the little figure was pointing, that was the output. That's the basic structure of a computer. And that's really the big takeaway here. Long before we had silicon chips or digital code, people were building machines that could compute using motion. The south-pointing chariot wasn't just some clever navigation tool. It was a physical machine that brought a mathematical principle to life. It was truly one of the world's very first analog computers.
It's just an incredible piece of history that really shows you how deep ancient ingenuity could be. And it leaves you with this really fascinating question. If a machine this sophisticated existed almost 2,000 years ago, what other ancient computers might still be out there, buried in old texts, just waiting for us to rediscover them?